going to be the omega? Infinity. This is a constant term, right? It's or something like that. Okay, yeah? This is something. For example, 5, 4, 4.2. This is a number, right? So here, if t is 0, omega is going to be infinity. Right? Let's put the point here. If t is infinity, how much is omega? 0. So it's going to be something like that. This is the characteristic of the machine. Now, can you tell me how the drill works? What is the relation between what is drilling? How many of you have done drilling? You have a drill and you're drilling, you get something hard, it's not going to rotate very fast, right? And it's going to start to make big noise. Very, very big noise, right? Look at here. What's going to happen? When it's not rotating very fast, where are you? Here, right? You have reached a very hard material, right? You need a huge torque to rotate the shaft, right? Right here. The speed is pretty low, and the torque is pretty high. You get to the chalk, so the drywall. You're going to go right away, right? It's not going to even start. It's not going to stop. So the speed is pretty high, right? And the torque is pretty low, right? So this is how it's characteristic of the drill board. Not just a simple drill. The one they use it for digging wells and those kind of things. They need this same kind of characteristic. If they hit a hard material, they cannot rotate fast because they have to go through. What you need higher torque, right? So you need kind of characteristic like this. When your rotation speed is going to slow down and come down, you need a higher torque to push it through, right? So this characteristic very good. That's one application.
Oh no.
So these are kind of characteristic, to see how they do look like. Series motor, they're a little bit different. The one they use it for shaving, shaving machine is also kind of similar to the series machine. They call it universal. They are AC machine, but their characteristic is kind of similar to the series machine. They are AC. You can see you can plug them to the wall. That's the AC voltage, not DC, but it's very similar to the AC machine. So I am almost done with analyzing the DC machine. There is one more complicated. I'm not going to go through the details, but I'm going to explain it how they structure them, how they work with them, and to see it's a kind of combination of a shunt machine and series machine together. They call it compound. So I'll talk about the different combination they have, how they do work, basic, not equation. I'm not going to go through the equation. Equation, you guys can do it yourself. I put one of them on the board. You can see, maybe I'll give you one homework. You can go through the equation to play a little bit more with the equation. But let's see what they are, how do they work, and one of the circuits, for one case, I'll put the circuit together, and we are done with the almost DC machine. The last part of DC machine would be the starting of the DC motor. That's the motor starter, We'll talk about that after the compound machine. And let me start from there.
Yeah. That graph you said was a characteristic of what machine?
This one?
Yeah.
This is we're working on the series motor, right? This is the torque, speed versus torque. As I say, as a generator, you are looking for the V terminal versus current. I know that one you can see over there. For all the motors we went through, V terminal versus the I load is important. We call it the load characteristic of machine. If they are motor, speed versus usually torque versus the speed, but now here we put the speed. Speed versus torque is important. So these are, we can see the difference between the motor and generator. Generator, VT versus IL, motor, omega versus T. These are the two important. Now, let's go over compound machine. Compound connection. See, all the compound means there is more than one, right? You are mixing something with something else, you call it compound. So up to here we had a shunt and we had a series machine, right? We had either the winding or separately excited, right? Here there are two excitations in the system. So just I'm going to put it like this. Let's say this is the armature of the machine, and this is one of the poles, right? Basically, there is another side here. I'm not drawing the other side. Just I'm doing it. For example, if I'll call this one N shunt, I call this one N shunt. This is exactly like a shunt machine. There is one winding like that. Let me, before going there, if you go back to the shunt machine, look at this one. This is the armature, right? This is the armature, right? This is the armature, right? So when you have a shunt machine, see, one is connected here, right? And the other one is connected here, right? Right or not? See, this one is the armature circuit, right? Just I put the R8 inside, right? This one and this one, right? And this is the shunt machine, shunt winding. One side is connected to this one, right? And the other side is connected here, right? This is the connection of the machine. Now here I'm saying again, one winding is exactly like this. It's going to connect like this. But I have series winding also. If you go back to the series excitation, it was like this. Look at here. This is a series. If you are going to draw the circuit, series, this one is going to come connect here, right? This one is going to come connect here, right? And this is the output of the machine, right? The excitation is in series with the armature, right? So the compound has a two windings for excitation. One is a shunt, one is a series. And usually the series has a very, very nice. Shunt usually has a lot of turns. If you are going to look at the dimension, physical dimension of the winding. Shunt winding, it has a lot of turns. Why? Can you tell me? Why it has a lot of turns? Let's see. If you remember, shunt winding is parallel with the voltage, right? If the more winding, the more turns, the higher resistance, right? If it's 1 ohm, think about it. So you connect it to the 100 volts, it's going to 100 amps is going to go through the winding, right? So you need not that much current. You need maybe 1 amp, 2 amps, to say to the shunt winding to magnetize the machine, right? So you have to have a high resistance, right? So shunt winding usually has a high number of turns. How about the cross section? Is it big or small? Why is small? Higher resistance, right? But now let's look at the series winding. It cannot have many turns. Why? This is in series with the armature, right? Armature current usually is high, right? If you put a big resistor in series with the armature, for loss, right? Loss. No, not good, but loss. It's a really bad machine, right? So series winding, it has usually a few turns. How about the cross section of conductor? Large, because it's going to carry a big current, right? Armature current, you know. So basically, if you look at this one, maybe this one has 100 turns. Just you kind of idea, you know, what is it? This one, for example, shunt has like 100 turns. Series has maybe 3, 4, 5 turns, something like that, right? So in general, there are two windings, right? So each of these windings, they are going to generate their magnetic field, right? So there are two cases. They can help each other, right? For example, this one is going to generate the. For example, this one is going to generate. Let's look at it here. For example, the way I put it here. If the current is going this way, this one is going to generate the flux this way, right? Let's say phi shunt here, right? Now look at this one. If I put the current also here this way, this one also is going to generate this way, right? This is the phi series, right? They're helping each other, right? They call it cumulative shunt. They're helping each other, right? But, so the resultant flux, if you look at it, is the phi shunt, right? And is the phi series. You know, just I put it this way to see. Phi shunt is the dominant part. Phi series is going to a little bit add to it. Or, if I put the current this way, it's going to reduce it. So, can you tell me what I'm doing here?
Creating a variable machine.
Creating variable field. The machine, variable field.
Yeah.
So basically I can control my field, right? So the main one is here. The main one is my shunt. Now, with my little bit extra or it's adding or reducing, I can control this flux a little bit, right? So this is kind of iterative variable flux. Right?
You can change the two bodies and one conduit of components and one can
No, I'll tell you what's the main advantage of this one. We didn't talk about the armature reaction and those kind of things. An armature reaction, you know, I think I'm going to bring finally one slide, you know, Tuesday to talk about that one. But armature reaction depends to the armature current. When the armature current is high, the armature reaction is worse, right? So this one, series, is going to be in series with armature, right? That was the reason we called it series, right? It carries the armature current, right? So the field is generating this one is based on how much armature current we have, right? If there is no armature current, it's almost zero. Looks like this one is not there at all, right? This is not generating that much of field. When the armature current is high, it's causing problem. This one is going to come to help us, right? This one is the extra element here, which is changing. Automatically, it's changing the flux with the armature current. When armature current goes up, the flux generated by this one is going to go up, right? When the armature current goes down, the flux generated by this one is going to go down. The main thing is the shunt, right? The main thing is the shunt here. Shunt is not going to change. But this PSH is going to get affected by the armature reaction. We want to try to compensate that one, you know what I'm saying, automatically. To do that one, we put extra winding here, which is instead with the armature. So basically this one is going to generate a variable flux, right? Based on how much current you have in the armature, right? So you can see the series machine, they are not good for the generator, right? Look at that characteristic over there, it's not good for a generator. But to get rid of, so I cannot put just series here because it's not going to be a good generator. The good one, they are either the separately excited or shunt. But the separately excited, it needs its own excitation system, right? Extra money. If I use shunt, I'm going to use the same, I don't need an extra source, right? I can use the machine itself to support it. But what's the problem with the shunt? This armature reaction is going to cause the problem. I can bring somebody to help me to kind of compensate the armature reaction. So, but in general, in compound machine, we have a two excitation winding. One is shunt, one is the series winding. So either they can help each other or they can be against each other. If they are helping each other, we call it cumulative shunt. In this case, see this current is going this way. So basically phi is a phi SH plus phi S. We call this one cumulative shunt. So you could have this case. Look at here. Again, let's keep this one here. I'm not going to change the shunt. This is the phi SH. And let's keep the series here and put the current here. So this one is going to be like this. This is a phi S. So the total flux here is going to be phi SH minus phi S. This is a differential compound, cumulative compound. Two cases, differential, and cumulative. Now, remember when we say shunt, I don't have shunt here. We said we have shunt, this is the armature. Why did we call it shunt? Yeah. Because this one was parallel with this one, right? But keep in mind, in the compound, there are two excitation winding, right? So this one can be here, right? In series with armature, and this one can be connected here. See, I have two. One is in series with armature, right? And this one here. They call this one long compound because this is just naming. You know what I'm saying? The series winding and armature, they are series, and shunt is going to be here. Or, I'm going to put all of them on the board. Or, it's going to be connected here, right? They have two windings. Shunt would be parallel with the armature circuit, and the series is going to be here. They call it short compound and long compound. So I'm going to put it all on the board, you know. All this. I'm going to put it in the middle board. Cumulative, differential. This is the last topic we are going to motor starter. I'm going to explain to you the example. You know, there's going to be one example. Yes.
How is it that you'd be able to change the direction of the current in this series winding?
How the current go that way? That's very simple. You know, it's gonna we will do it once. You cannot change it anymore. But you know, let me for it.
So you're saying that it's in the setup?
Yeah, it's in the setup. Exactly. So you can do it here. So this one, for example, is going to come connect here, and let's say it's only this path. This one is going to be here. So this is the armature path, right? If you want to go other way, just move this way, right? Now the current is going to be. That's in the setup. Yes, exactly how you do it. So basically, we're going to have 4 total cases. Let's see what 4 total. We call it short cumulative, short shunt cumulative. I have my armature. I'm going to put it this way. No, this is the RA and LA together. Just like put it as a winding. RA and LA. Now we say short. If it is